This video starts us on the subject of thermodynamics, energy in motion. Energy in motion, and we'll be talking about some of the basic laws in this video and some of the basic calculations for work. And future videos we'll talk about heat engines. But here is a heat engine, steam engine, and some type of fuel, wood or coal, to create high temperature for the water, create steam to push the pistons back and forth and drive the wheels, and lots of fun. A little bit smoky, but historical. So we're going to understand sort of the development of thermodynamics and how scientists became interested in doing the research to enhance the efficiencies of these heat engines. So let's continue. Boiling tea kettle. Again, there's a source of energy down here, a hot stove, and the water boils, creates steam, makes a whistle, and you know the tea is done. Right, so we have a law of thermodynamics, first law of thermodynamics. It's really a statement of conservation of energy for the symbols, the quantities that are useful in studying heat engines. So the first law says that delta U, the change in the internal energy of the object, and we can have kinetic and potential, energy is internal, but the change in the internal energy is equal to the heat, that's positive if energy comes into the system, minus the work that the system does, and the work is positive if the system is doing work. So change in internal energy is related to Q minus W. And I just ask you if you think this sounds reasonable. This internal energy is related to temperature of the system, and we'll talk about that in the future. But we have heat here. If more energy comes into the system, is it reasonable that the internal energy will increase, given that W stays constant? So if Q increases, more energy is coming into the system, and the work done by the system is a constant. Yes, we should expect the internal energy to increase. Or another example, if Q is constant and the system does more work than some previous case, if W is a larger number, the system's doing more work, that's going to require energy to do that, and some of the internal energy supply is being used up. So statement of conservation of energy. This does not make any kind of prediction as to the likelihood of something occurring. It's just a statement of energy balance. Energy in minus energy out gives us the change in the internal energy of our system. And there's some drawings here. Our textbook uses these kind of wavy arrows for the Q, for the energy. Here energy is coming in, work is going out, and we get some relationship with put particular numbers on these. If Q comes out of the system, then Q will be a negative number if energy is coming out of the system. And also, if the system is worked on for a gas, if we're compressing the gas, we're doing work on the gas, then W will be a negative number. So you must learn to recognize when Q is positive, when W is positive. Q is positive if energy goes into the system. Q is negative if energy is withdrawn from the system. W is positive if the system does work, and that we'll mainly talk about gas systems here, so that's going to be the system expanding, and we'll have the system doing work. If we're compressing the gas, then W will be a negative. So some numbers apply to this. So we have a situation where we have 40 joules of Q energy coming in. We have minus 25 joules because this is 25 joules leaving the system. And there's work done on the system of 4 joules. The system does work of 10 joules. So we'll take a look at the net values here. For the Q, there was 40 units as positive, minus 25, so we have positive 15. For the case of the work, we have 4 joules of work being done on the system, but the system does 10 joules of work, so that's a plus 6 for the W value. In the calculation for delta U, there's a minus sign between Q and W. So delta U is Q minus W. We've got 15 minus 6. So we've got a net gain of 9 joules. The internal energy goes up by 9 joules. In the situation over here, we're extracting 150 joules from the system. By some means, don't care how we do it, but 150 joules leave the system, and we're doing work on the system of 159 joules. Now Q minus W, Q is a negative 150. Again, this minus sign is present in the formula, so we keep it here. W itself is a negative number. Work was being done on the system. The system is contracting. The volume's getting smaller. The work is minus 159. Double negative here makes this turn positive, and we have a net of 9 joules. The internal energy will increase by 9 joules. So delta U is Q minus W, a statement of conservation of energy. And the universe, things in the universe obey the law of thermodynamics. So our body temperature is usually higher than room temperature. 37 Celsius for body temperature, 20 degrees Celsius for kind of an average room temperature. So there's going to be energy going out. We might lift some books. We might move our pencil across the page, doing work, taking notes, working homework problems. We might walk around campus for a study break. The body does work. And in the law of thermodynamics then, this Q is a negative number, this work is a positive number, and our internal energy would run out unless we resupply ourselves with energy from food. So there's another input here. It's not labeled Q, but food energy helps us maintain our body temperature above the temperature of the environment, and we're able to do work because this food gives us a resupply of our energy. And plants absorb sunlight, that's a Q going in. They have Q going out in the processes that they undergo. We're not going to talk about either humans or plants, but thermodynamics can be applied. So, basics of a heat engine. And we're missing a couple basics here, but the working part of the heat engine, there's energy that comes in, there's work that goes out, and there's energy that's rejected to some cold reservoir. Now in this drawing, I would add in a cold reservoir down at the bottom here for this energy coming out of the heat engine to move into a cold reservoir, low temperature reservoir. And then there is a high temperature reservoir up here. For heat engines, we burn wood, we burn coal, we burn oil, we capture the energy from radioactive decay, whatever the means is, but we create some high temperature reservoir up here. And then Q sub H, that's the energy that's leaving the high temperature reservoir. And I'll often refer to Q sub H here. And Q sub C, that would be the energy going into the cold reservoir. But the names here are fine. Qn is coming into the heat engine, the working machinery is here, and we'll talk very little about the details of how to build a heat engine. We're just focusing on the energies in this discussion. Q out, energy that leaves the system, and then work is positive. Energy also leaves the system here. And in a idealized case, the amount of energy that comes into the system equals Q sub out plus W. There's a conservation of energy here. Our energy supply, this Qn, there's no source of energy in the heat engine itself. The energy is moving from the high temperature reservoir towards the low temperature reservoir. That's the way our energy naturally moves. And we're capturing some of that in some mechanism, this heat engine. A portion of the energy from the high temperature reservoir becomes useful work. And there is a law of thermodynamics. It's impossible for the Q out to be zero. We always will lose some energy to this low temperature reservoir. So we just have to live with that. That's the way reality is. We can try to minimize this. We can make our heat engine more efficient by having W be larger and Q out be smaller, but we'll never get Q out to be 0. So let's make that statement again in the future. Something else to realize here, we're mostly going to talk about gas systems with this heat engine, and there's a way of describing the state of the system, and that would be to describe how much internal energy there is, what is the value of U at some point in time, to describe the pressure and the temperature and the volume and the number of molecules in the system. Those are called state variables. They give us the state of the system. U, the internal energy, P, the pressure, T, the temperature, V, the volume, and N, the number of particles. Now Q and W are going to change some of these state variables. The pressure, the temperature, the internal energy and such, they're going to be different. And we'll go between different states, and there are different ways, there are different values of Q and W that will change us between two energy states of a system. A little question: suppose that the internal energy of the system is desired, we want to know what the change is, and we put 300 joules into the system, and the system does 200 joules of work. What's the change in the internal energy? Well, delta U equals Q minus W. We perhaps go back to that. Delta U equals Q minus W. So we're saying that we deliver 300 joules to the system. The system does 200 joules of work. So our net is 100 joules. There was more energy coming in than what went out in work. So the delta U will be plus 100. The internal energy will go up by 100 joules. So let's keep on going here. So tying in some of the older concepts too regarding pressure, force, and area. When our gas system is confined to a cylinder and we have a movable piston that can go up and down, so we're looking at perhaps the piston in a gasoline engine and the crankshaft down here that receives this mechanical energy. So we have Q coming in. Maybe we burn gasoline in the cylinder and we release energy here. That's going to create extra pressure in the system, and that pressure acts over an area. There'll be a force on this piston to move it. And in engines, we get a repeated cycling of the material and the mechanical parts around and around. So burn gasoline, we exhaust gasoline to the Q out, push out the byproducts, and then we pull in fresh air and fresh gasoline, get ready to go through another cycle. But the work is being accomplished by a force creating pressure, and we're actually going to calculate the work done in simple situations. If the pressure is constant, the work will be the pressure times the change in volume for the system. And this gets us into force times distance. Force is pressure times area, and then if we multiply that force by a distance, we'd have an area times a distance. That's a volume. So ask your instructor to clarify that, and I'll clarify it for my students. But here's a diagram that might help you think about this. We have gas in here. Molecules are bouncing off of the piston. We put in more energy, and that will increase the energy in our system. The molecules travel faster and bounce off with more force from the bottom of the piston. So our force is pressure times area. We're going to have the ability to lift this piston with enough force being present as we put in more energy. Work is force times distance. Work can be calculated as pressure times area times distance. And this area times the D gives us a new volume, an increase in the volume. So the old piston is the dotted line that's position. And as this force pushes up on the piston, there's a force times a displacement. There's work being done. And it turns out we can calculate this with pressure times delta V. So what's the requirement in using this? When is it allowed to use work equals pressure times change in volume? And you should be saying pressure has to be constant. So we'll have to run this system in a well, contrived way for this to be true, but the pressure has to be constant to do this calculation. On a graph, we can say that the work done is the area under the curve. So here we have the pressure being constant. This is called an isobaric. Barometer, the baric root is in there. Barometer deals with pressure. Isobaric, constant pressure. So from point A to point B, we have constant pressure. We can use our formula. Work is equal to the pressure in pascals times the change in volume in cubic meters. That would be our work done. If we have a curve, if the pressure is not constant, we can approximate the work done by putting in many rectangles and calculating the area of each rectangle and sum those up. And that would give us an approximation for the work being done. We can run this change of volume in two directions. If the volume is increasing, then the system is doing work. If the volume is decreasing, then something is working on the system and the work will be a negative number. So just be ready for that. If the pressure occurs, if the process occurs at a higher pressure, I should say, then the work is a greater number. So here we have a process that starts at A. One choice is to go to B conditions, state of the system, and then drop down to C. Another choice is go from A, change the state of the system down to D by moving at constant volume, lower the pressure, and then we have a movement out to C. Which one will have the greatest work? Going A, B, C, or A, D, C? Well, work is area under the curve. This ABC is going to have the greatest area under the curve. The work is being done here at higher pressure. Work is equal to pressure times change in volume. So P delta V is going to be bigger for this AB path than for the DC path. The pressure is lower here. We can create a cycle. We can go around a cycle. If we start at point A, have some change in volume going to point B, and then maybe we take energy out by letting the system do work. And we drop down constant volume down to C. As energy comes out of the system, the pressure will drop. And then we compress the gas from C to D at low pressure, not difficult to do. And then we compress the gas further, but now at constant volume, and the pressure goes up. So this would be a cycle. And the net work that is done in a cycle, you take the area underneath the high pressure curve, find that area. You take the area underneath the part of the process that occurs at low pressure and find that area. Then you subtract the two areas. The net work is the area inside the cycle, inside the boundary of the cycle. Again, working on a pressure-volume diagram. Pressure is the vertical scale, volume is the horizontal scale. If we don't have a square, maybe we have some processes that bring us around some kind of loop, or ellipse. Same principle. There would, if you could drop straight lines down to the axis here, the volume axis, and find the area underneath this curve, and then find the area underneath the straight lines and subtract, we'd have a net area here that would be the amount of work that is being done. So we'll deal with rectangles. We won't deal with curves in my particular course. But the net work is the positive work combined with the negative work. When the volume is decreasing, the work is a negative, and we would have the inside the rectangle here being the net work done by the system. A couple other paths. We can start at a certain set of conditions, a certain state, and label that here on the PV diagram as point A. We can have an isothermal change of the volume. Isothermal, constant temperature. Isothermal, constant temperature. We can change the system out to point B in that way. Or we can have an adiabatic change. Adiabatic, Q is equal to 0. Q is equal to 0. So we have isothermal, delta T would be 0 on this path. and adiabatic Q would be 0 on this path. So which one involves the most work? The isothermal path or the adiabatic path? And you should say isothermal. It has the biggest area under the curve. And notice too, what's happening, work is basically pressure times change in volume. On this path, the pressure is higher. Here the pressure is lower. The work is pressure times change in volume. So if you work this in the rectangle method, you'd have short rectangles here, not much area, bigger rectangles up to the path AB. But isothermal, being done at constant temperature, and as the system is expanding, something is going to have to supply us with energy to maintain constant temperature as the gas expands. The adiabatic case, Q is 0, so we don't have something maintaining our pressure as much, lifting up the energy of the molecules. We get to a lower value. And again, I'd ask you to remind yourself, where is temperature low in this PV diagram? Where is temperature high? PV equals nRT, ideal gas law. If T is low, then pressure, volume low, both of them low. So in this corner is the cool part of the PV diagram, and the upper right is the higher temperature part. The lower left corner is where temperature is small, upper right corner, temperature is higher. And we can draw on these isothermals and adiabatics and connect them in various ways and create cycles. Our fourth and last special path on the PV diagram, isochoric, a constant volume. Isochoric, constant volume. How much work is done on the path BC? You should say 0. Work is pressure times change in volume. Isochoric, the volume is constant, the change in the volume is 0. So there'll be no work in that path BC. Then thinking about the movement of energy, energy spontaneously or naturally will move only from a high temperature to a low temperature situation. So if we put two pieces of steel together, and one is at 200 degrees Celsius, the other is 120 degrees Celsius, energy is going to move from the hotter object to the cooler object. And that will always be the case. That is a law of thermodynamics, that by itself, energy will never move from a cold reservoir to a higher temperature reservoir. So just keep that in mind. Hope that makes sense to you. So just maybe to go back just a little bit here, there are mechanisms or ways of calculating the work done on a isothermal path. It involves a logarithmic calculation, and the work basically is how many moles are in the gas system times the gas constant multiplied by the temperature in Kelvin times the natural log of the ratio of final volume divided by initial volume. And I'll be working with that with my students. You have to ask your instructor if you're going to be calculating work for an isothermal. But you can't use P delta V because the pressure is changing. It's illegal to use work equals P delta V for an isothermal or an adiabatic path. And speaking of the adiabatic, what would the work be here? Well, we know delta U is equal to Q minus W. On the adiabatic, the Q is equal to 0. So the change in the internal energy is equal to the negative of the work. So here we're compressing actually on this adiabatic. So the work is going to be a negative number. And we have a situation here that the delta U will be positive. Delta U is Q minus W. We're compressing the gas, so work is a negative number, and the delta U will be a positive number. The gas is picking up energy, and that might be reasonable to you. It's moving away from the cold corner of the PV diagram, indicating that there's more energy in the system. Then might think about reversible and irreversible processes. In the real world, the processes we use are not reversible. There's energy loss to friction that can't be sort of rebottled up and put back to use for us. So idealized cycles can be reversible, but the real world, things are not reversible. There's friction and losses that can't be controlled to allow us to conserve as much energy as we want. Illustration here, car stopping with regular brakes that use pads rubbing on a rotor. That rotor increases its temperature, it's receiving the kinetic energy from the car, and then that energy dissipates out into the environment, and you can't use it to go forward again. A hybrid car works a little differently. The brakes engage electrical generators in the wheels, and those recharge the batteries that the car carries. So there's less waste energy for the hybrid car. Or think about a air tank here in a vacuum, and somebody breaks a seal on it, so the molecules from the air tank can go out into the room. We'll talk about disorder and naturally occurring events towards the end of this chapter, but let's just ask you now, do you have questions? If so, write them down, and your instructor, I'm sure, will be happy to answer them. That's where we'll stop in this video. We've had the sort of conservation of energy represented in the first law. Delta U equals Q minus W. The change in the internal energy equals the energy that goes into the system minus the work done by the system. There's some special processes on the PV diagram. Constant pressure processes, we can calculate the work. Pressure times change in volume. We have adiabatic processes where Q is equal to 0. Isochoric processes where the volume is constant and the work is 0. And isobaric processes where the pressure is constant, and there we get our easy calculation. So isothermal, adiabatic, isochoric, isobaric. You should be familiar with those terms and familiar with how you calculate the work in each situation. Signing off.